Okay, still talking about the structures of linear systems. In this next video, we'll be talking about the rank of a matrix. We already made mention of rank in the previous video, but here we are emphasizing the idea of rank. How do you find the rank of a given matrix? And all of that, that is what this video is meant for. In linear algebra, the rank of a matrix is one of the most important concepts. It's, it tells us how much useful information a matrix contains, right? So the rank is connected with linear independence, systems of equations, geometry, applications in science and data. This lesson explains the definition of matrix, how to find rank using row reduction, and actually the actual meaning of rank and some worked examples. So let's move on. Definition of rank. The rank of a matrix is the matrix number, is the maximum number rather, of linearly independent columns or rows. Okay. So that means that even from a matrix, you can already determine the rank. If you can clearly see that one is a multiple of the other. So it means that the rank the rank is not equal to the number of columns in that case. So the rank of a matrix is the maximum number of linearly independent rows or columns. Equivalently, rank is equal to dimension of the row space, and then that, or it is also equal to the dimension of the column space. So for a matrix A, the rank of A is the number of independent rows. So, and of course, like I said already, dependent rows are rows where you have one as a multiple of the other, right? And rank of A can also be the number of independent columns, depending on what you are focusing on. These two numbers are always equal. So number of independent rows is equal to number of independent columns, and that is equal to the rank of the matrix. So the basic interpretation is that rank tells us how much real information is in a matrix. If some rows or columns can be written as combinations of others, that is, maybe one is a multiple of the other, they are redundant. So only independent rows or columns contribute to rank, right? So rank counts the useful rows and columns. So rank is about the useful rows and columns you have in a matrix. So let's talk about rank from row reduction. So the most common way to find rank is by row reduction, or what we call Gaussian elimination. The principle is that after reducing a matrix to row echelon form or reduced row echelon form, of course, the row echelon form is that place where you just make sure that everything below the principal diagonal is zero, right? But reduced row echelon form is where you make the original matrix, you make it into a unit matrix. Maybe not necessarily a unit matrix, but things are a bit tighter in that case, like you have more things to do there, but most of the times they get to do the same job. So here, rank at the end of the day, after reducing a matrix to row echelon form or reduced row echelon form, rank is equal to the number of non-zero rows. So if you have a zero row, it doesn't form part of the rank. So all the rows that are not that are non-zero rows, that is, every element in the row is not zero. So if every element in a row is zero, you say it's a zero row. So even if you have a row where maybe you have three columns and there are two zeros and then a non-zero number, that is not a non-zero row. So you count that as part of rank, right? So we talk about elementary row operations, which I had mentioned before now. So, so the following operations do not change rank. Swap two rows. If you swap two rows, maybe row one becomes row two, row two becomes row one. That's fine. It doesn't change the rank. You multiply a row by a non-zero number, doesn't change the rank. You add a multiple of one row to another row, doesn't change the rank. So these operations are used in Gaussian elimination. And the procedure is you write the matrix, you use row operations to reduce it, you convert it to echelon form or reduce row echelon form, then count the non-zero rows. That number is the rank. So let's take an example. We've been talking. So find the rank of 1, 2, 3, 2, 4, 6, 3, 6, 9. Clearly, you're most likely going to have two zero rows here. Yeah, because 2, 4, 6 is a multiple of 1, 2, 3. 3, 6, 9 is also a multiple of 1, 2, 3. So step one, you can observe that you can observe the relations that row 2 is 2 times row 1, row 3 is 3 times row 1. So you can perform row operations now. So basically you can just say, of course, you want all these elements to be zero. Every element below 149. This 236 should be zero. So what can we do? So row 2 now, for row 2, the new row 2 here can now be the old row 2 minus the 2 times the old row 1. That's 2 minus 2 times 1. That'll be 0 down here. Then 4 minus 2 times 2, that'll be 0 here. 6 minus 3 times 2, that'll be 0 here. That's 6 minus 6. Then coming down here also, 3 minus 3 times 1. That's 3 minus 3, and that will be 0. Okay. like that. 6 minus 3 times 2, that's 6 minus 6, another 0. 9 minus 3 times 2, that's 9 minus 9, 0. You have two zero rows. So there's only one zero, non-zero row. That means the rank of this matrix is 1. And that tells you that the only thing that is giving you any meaningful information is the first row, right? So if you count now, non-zero rows, only one non-zero row like this. So the rank of this matrix is simply 1. So for example, 2 now. So for example, to see what happens, here you have 1, 2, 1. Find the rank of 1, 2, 1, 2, 3, 6, 4, 3, 5, 5, like that. So first you do row up reduction. So you have 1, 2, 1 here, right? Then for this now you can say 2 minus 2 times 1, that will be 0. 3 minus 2 times 2, that's 3 minus 4, which is minus 1. 4 minus 2 times 1, that's 4 minus 2, which is 2. Then coming down here now, you can have 3 minus 3 times 1, that's 3 minus 3, 0. 5. All right. 5 minus 3 times 2. That's 5 minus 6. You have minus 1 also. Then 5 minus 3 times 1. That's 5 minus 3, which is 2 down here. So we still continue we still continue. So this is a new matrix now. So with this pivot now, you want to make sure this is also 0. So what do you do? So we have 1 to 1 here. So we also have 0 minus 1, 2 like this. Then we do eliminate again. So, and to do that now, because we want this place to be 0, we can say row 3 minus row 2, right? So 0 minus 0, 0. Minus 1 minus minus 1, that's minus 1 plus 1, which is 0. 2 minus 2 is 0. At the end of the day, we have a 0 row, which is this one. So the rank of this matrix will just be 1, 2. There are two non-zero rows, even though there's 0 here, but the whole row is not 0. So when the whole row is 0, you say you have a 0 row, right? So there are two non-zero rows. So it means that the rank of the matrix is 2. So count non-zeros, that's 1, 2. Two non-zeros, that means the rank of this matrix B is equal to 2. Now, let's talk about a full rank matrix. That is where the matrix is fully all the rows are non-zero. In that case, now you can get a closed solution. So you can get a fixed solution like that, not infinitely many solutions or no solution even. So find a rank of 102, 1013, 214. Of course, I guess I have to go and do the row reduction because something must have been skipped here. 102, 013, 214. 102, 013, 214. Okay. 102, 013, 214. So we want to find the rank of this matrix. So do row reduction as usual. So row 1, row 2, row 3. So this is one, we need this and this to be 0 first. Generally speaking, we want everything below this principal diagonal to be 0. Okay, but you do step by step. Make sure these two are 0 first. This is already 0, so you can only focus on this now. So it means that row 1 and row 2 are going to remain what exactly they are right now. So you have row 1, you have row 2, and row 3 now is going to be the old row 3 minus 2 times the old row 1 as usual. So you have 102, 013 fixed. Then you have 2, this 2 here, minus 2 times the 1 up here. So that's 2 minus 2, which will be 0. Okay, so this is 0 now. Then come to this one. 1 minus 0 is 1. Then 4 minus 2. Oh, sorry. It's 2 minus 2 minus 1, right? So this has got to be 1 minus 2 times 0. So 2 times 0 is 0. So 1 minus 0 is still 1. Done. Then here you have 4 minus 2 times 2. So 4 minus this 2 here, 2 times this 2. So that's 4 minus 4, and that is also 0. Okay. So that's definitely not the end. We have to keep going until we get everything we need to get. So the next step now, we can come here. So so we have this pivot, we have this pivot. So this has got to go to 0 now. So let's see how that works. So it means that row 1 remains row 1 again, row 2 remains row 2, but row 3 it's now going to be, for this to be 0, we have to say the old row 3 minus the old row 2. So that means we have 102, 013. Then coming down here, we have 0 minus 0, 0, 1 minus 1, 0, 0 minus 3, minus 3. Okay? So what else can we do? Well, we want to do this in echelon form or something, but even this is enough because what the answer that we have here, this answer here is a unit matrix. It is reduced row echelon form. But even without the reduced row echelon form, we can still conclude that this is not because now we have it in echelon form. So either in echelon form or reduced row echelon form, we can already say this is a full rank matrix, meaning that the rank is 3 because columns all the columns are good, all the columns actually there's no zero rule. But let me take it to reduced row echelon form. Maybe this is an opportunity to do that. So for reduced row echelon form now, we need this place to be 1, all right, and this 2 will have to be 0. Okay, so let's do it step by step. So let's first of all make this -3. Let's make it 1. So that means that row 1 will remain row 1, row 2 will remain row 2, but then row 3 will have to be -1/3 times the old row 3, so that this can be 1. So we have 1, 0, 2, and this is 0, 1, 3. And lastly, this is 0, 1, 3. And lastly, we have 0, -1/3 times 0, 0, -1/3 times 0, 0, -1/3 times 1/3. That will simply be 1. So that's this next step. So that's that step. So the next step now is we need to make this and this 0. So what do we do? So it means the row 3 now is fixed, but row 1 will change. So the new row 1 is going to be the old row 1, all right? The old row 1 -2 times the old row 2, -2 times the old row 3. The old row 3 now is 1 here. Then the new row 2 is going to be row 3 minus the -3 times the old row 1, so that we can have 3 minus 3 times 1. So this one would have been 2 minus 2 times 1, right? So, and finally, row 3 remains what it is. So row 3 is still row 3. So what do? We have 1. So for this, we have 1 minus 2 times 0. Okay. So this is simply 1 minus 0, which is 1. So this is also 0 minus 2. Oh, okay, no. This is not the issue. 1 minus 2 times 0 here. That's this third. We are talking about row 3. Then this is 0 minus 2 times 0. That's still 0. Then here 2 minus 2 times 1. So this 2 minus 2 times this one, that'll be 2 minus 2, and that is also 0. Okay? Then next, you have for the new row 2 now is the old row 3. The new row 2 will be the old row 2, all right, minus 3 times the old row 3. That's what this should be, yes. So so for this now we have 0 minus 3 times 0, that's 0. 1 minus 3 times 0, that's 1. 3 minus 3 times 1, that's 3 minus 3 times 1. That's 3 minus 3, and that is 0. Okay? Row 3 remains what it is. That's 0, 0, 1. So you see, this is non-zero, this is non-zero, this is non-zero. So that means that the rank of this matrix, the rank is equal to 3. So in that case, you say it's a full rank matrix because the number of rows is equal to the number of non-zero rows. So all rows are non-zero. So the rank of this matrix is 3. So you say this matrix is full rank. Okay? The matrix is full rank. So let's talk about the geometric meaning of a rank, right? So consider rows as vectors. If you consider each row as a vector, rank describes the dimension of the space they span, right? So rank 1, all vectors lie on a line. Rank 2, vectors lie in a plane. Rank 3, vectors fill three-dimensional space. Okay? Line, plane, space. That's how that goes, each rank. So that's why anytime if in a 3 by 3 matrix you have all vectors, just that the rank is 1. So you have everything collapse into a line. If you have 2 instead of 3, vectors lie on a plane. But if you have everything, so the whole space is filled up. So imagine this now. You have 1, 2, 3, 2, 4, 6. Of course, because this is a multiple of this, row 2 is 2 times row 1. So the vectors will lie on a line because the rank of this matrix is just 1 in that case. Then we can talk about rank in linear systems. They are very useful also there. So consider the system AX equals B. Rank determines the type of solution. We are talking about structures of linear systems here. So rank determines the type of solution. So imagine case 1 now. You have unique solution if the rank of a matrix is equal to the number of variables. So, okay, let me even flash everything at once. Okay, so you have unique solution if you have every full rank matrix has unique solution. That is, you don't have infinite many solution and everything. So if the rank A is equal to the number of variables, then you have a unique solution. Case two, you have infinite solutions if the rank of the matrix is less than the number of variables. All right. I mean, that tends to correspond with the fact that, okay, you have three variables and one equation, three variables, two equations. Then most likely you're not going to have you're going to have infinitely many solutions. Of course, you can have three variables and three equations and still have infinitely many solutions, but those ones are guaranteed. So usually when the rank of a matrix is less than the number of variables, you're going to have infinitely many solutions. Case three, no solution. So that means the rank of A is not equal to the rank of either A or B, like that. It's not equal to, yeah, it's the rank is not equal to anything you know. I think that's the best way I want to say that. So example, talking about system of equations, you have x plus y equals to 2x plus 2y equals 4, right? So um they are basically the same. So you have 1, 1, 2, 2. So row 2 is 2 times row 1 already. So the rank is simply going to be 1 because the second row doesn't give you any special information, right? So the number of variables is equal to 2. So infinite solutions exist in this case because the rank is 1, whereas you have two variables. So you have infinitely many solutions. So let's talk about meaning of rank in terms of applications. Okay. So imagine in data and science, rank means the number of independent features. So rank is the number of independent features. So low rank means high redundancy. So imagine you have uh, 10 independent features and the rank, you now do rank of the matrix represented by those features, and the rank is now like 3. So that means that there are so many, like seven of the variables are useless, like they don't add any information to the system. So I think one comparison you can do with that with statistics in that sense is the fact that so many of the variables they are correlated. So if they are correlated, that's one thing we do in data science. We can eliminate highly correlated variables. Or maybe we also talk about something like collinearity, because those ones they are going to cause noise in the system because they are basically about the same. So you want to remove those kind of things so that you can retain only what adds something meaningful to your data. So rank is number of independent features. Low rank means high redundancy, and you can use that idea in machine learning, just like what I've described. Then statistics, engineering, and signal processing. If I want in the machine learning we do is feature importance. So we do some analysis to see which of all these 10 variables, which ones are the most important. So you want to relegate things that bear resemblance to themselves. You want to relegate them as much as possible. So if one column depends on others, of course, rank will decrease. Or they are highly correlated. That one increasing means the other is also increasing. So that's going to cause some redundancy. So let's talk about properties of rank. There's the idea of maximum rank. So for an m by n matrix, so the rank of A is usually less than or equal to the minimum between the number of rows or the number of columns, depending on whatever you're considering. Then for zero rank, if all entries are zero, then the rank is zero, because rank is the number of zero rows rather, after you have done row echelon, you have made the matrix into row echelon form or reduced row echelon form, anyone you choose. Either one will give you the answer. Then you say a matrix has full rank if the rank of A is the minimum of either M or N, depending on whether you're following the rows or the columns. So in that case, you say the matrix is full rank. And then we talk about rank and determinant. So for square matrices, right, if the determinant of a matrix is not equal to 0, then it means it has full rank. Okay, so we are still going to talk about that in terms of singular and non-singular matrices. So if the determinant is not equal to 0, then the rank is full. But if the determinant is 0, the rank is less than n, right? So there's that connection between rank and determinant. And of course, that also has other things, like if the determinant of a matrix is not equal to 0, we know that the matrix will have an inverse, and if it has an inverse, it's going to have a unique solution, right? But if the determinant is equal to 0, you have a singular matrix and it doesn't have a unique solution, or maybe it doesn't have solution even at all. So in summary, we have this, that the definition, we're talking about rank of a matrix. We have the main idea is you're talking about independent rows and columns. That's rank. The method, you can use row reduction. Calculation, you count non-zero rows. Geometry, it talks about the dimension of space. For systems, it determines if you're going to have solutions or not. And the maximum is the minimum of number of rows or columns, depending on whatever you're focusing on. Okay. So if you have a 2 by 3 matrix, for instance, if you have a 2 by 3 matrix and you're focusing on rows, so the matrix would have had full rank if the rank is 2. If you're focusing on columns, the matrix would have full ranks if the rank is 3. So depending on what, but most times you just focus on the rows. So the final formula is that after row reduction, rank is equal to number of non-zero rows in echelon form. This is the main practical rule for finding rank. So reduce to echelon form and then count the non-zero rows. So find the rank of each matrix using row reduction. Okay, let me show this in 2s like before, or maybe 3s if possible. Yeah, I can do 3. So, of course, we can see here that the rank of this is most like is 1 because this is a multiple. 2, 4 is a multiple of 1, 2. Then the rank may be 2. I don't know. Okay, maybe I can quickly do that. 1, 3, 2, 5, right? 1, 3, 2, 5. What is the rank of 1, 3, 2, 5? Okay, so let's say we have 1, 3, 2, 5. We need a rank. So this is row 1, this is row 2. So we can make this into, we need this to be 0. So we have row 1 remains. Row 2 now is going to be the old row 2 minus 2 times the old row 1. So we have 1, 3, then 2 minus 2 times 1. So that'll be 2 minus 2, which is 0. And this is 5 minus 2 times 3. That's 5 minus 2 times 3, which is 5 minus 6. That's minus 1. Okay. So, I mean, at first sight, we can already see that this is not a multiple of that. So most likely it's going to have full rank. Well, this is echelon form. You can leave it in this form. But if you want to take it further, you can still take it. But it doesn't change anything. So already, once you make all the numbers below the principal diagonal 0, like, which is only this one in this case. So we can already see that the rank of this one is equal to 2. So the rank of this matrix is 2. So it is a full rank matrix. It has two rows and it has a rank of 2. So that it's a full rank matrix. So if you solve this kind of problem, now you are most likely going to get a solution. So this one, of course, 2, 4, 6 is a multiple of this. So the rank is most likely going to be 2, because this 2, 4, 6 is redundant because it's a multiple of 1, 2, 3. Then we have 4, or 4, 5, 6 now. We have 2, 4, 6, 1, 2, 3. So in fact, the rank here is going to be 1 because 2, 4, 6, and 3, 6 now multiples of 1, 2, 3. And when you come here, 1, 0 to 2, 1, 3, 2, 1, 5. Maybe I should do this one now because none is a multiple of the other. So let's see how it is for 3 by 3. 1, 0, 2, 2, 1, 3, 3, 1, 5. 1, 0, 2, 2, 1, 3, 3, 1, 5. So 1, 1, 0, 2, 2, 1, 3, 3, 1, 5. Let me confirm and be sure about that. 1, 0, 2, 2, 1, 3, 3, 1, 5. So we want to find the rank of this matrix. So we do the echelon form. So in this case now, this should be 0. So maybe I shouldn't worry again trying to do all those fine details because we have done that a lot. So we have 1, 0, 2 here. So if we need this to be 2, that'll be 2 minus 2 times 1. That'll be 0. 1 minus 2 times 0, that is 1. 3 minus 2 times 2, that's minus 1. That's 3 minus 4. Then coming down here, we have 3 minus 3 times 1, that's 0 also. That's 3 minus 3, 0. Then here, 1 minus 3 times 0, that's 1 minus 0, 1. 5 minus 3 times 2, that's minus 1 also. That's 5 minus 6, that's minus 1. So next, we need this to be 0, you know. So if in that's for row echelon form. Right. So next, we need this to be 0. So we just have row 1, 1, 0, 2 the way it is. Then row 2 also remains 0, 1, minus 1. Then for row 3 now, we can just have subtract row 3 minus row 2. So that's 0, 1 minus 0 minus 0, 0, 1 minus 1, 0. Minus 1 minus minus 1. That's minus 1 plus 1, which is also 0. Okay. Onyx. So though it's not obvious from the matrix directly, but this still shows that the rank here is 2. Okay. Rank is equal to 2 because we have 1, 0 row. Okay. So the rank of this matrix is 2 like that. So but I mean, so there's the obvious one and there's the one that is not so obvious. The obvious one is this one where you can see the multiples, but here you can't see multiples. But until you do row reduction, you may not know what exactly is happening there. So 6 may also be like that. From here, I can already see that the rank of this is most likely going to be 2. You may have to do some switching and all that to get that done. Okay, so okay, we have a 4 by 4 case. I'm tempted to do that. Let's see. Okay, 1, 2, 1, 2, 3, 4. Okay, this is a multiple of this, so most likely the rank is going to be 2. It can be 1 too, but until you do it, you don't know. So it can also be 1. All right. Okay, maybe I think I'm tempted to do this other one. 1, 2, 3, 2, 5, 8, 3, 8, 13. 1, 2, 3, 2, 5, 8, 3, 8, 13. 1, 2, 3, 2, 5, 8. 1, 2, 3, 2, 5, 8, 3, 8, 13. So want to check the rank. So again, I mean, we've been doing this a lot, so I won't just waste my time talking about it too much. So of course, row one remains row one, 1, 2, 3. So we want this to be zero, we want this to be zero first. So 2 minus 2, I mean 2 minus 2 minus 1, that's zero. 5 minus 2 minus 2, that's 1, that's 5 minus 4. 8 minus 2 times 3, 6. That's 8 minus 6, which is 2. Then coming here, we have 3 minus 3 times 1, that is 0. Then 8 minus 3 times 2, that is 8 minus 6, that is 2, right? That is 2. Then 13 minus 3 times 3. That's 13 minus 9. So this is 4. So, okay, I can already see redundancy coming, but it's okay. We'll keep working at it. So next, I want this to be 0. Okay, if I want that to be 0, so I have 1, 2, 3. Okay, 1, 2, 3. Then this is 0, 1, 2. So we have 2 minus 2 times 1. That will be 0. So 0 minus 2 times 0 is 0. 2 minus 2 times 1 is 0. 4 minus 2 times 2 is also 0. So that's how we see this now. So the rank again is 2. Okay, the rank is 2 because we have one non-zero row. I mean, we have one zero row rather, one zero row. So the rank is the number of non-zero rows once your matrix is in echelon form. So with that, we come to the end of this interesting video talking about the rank of a matrix, and we've seen how useful that is. So form your matrix, reduce it to row echelon form or reduce row echelon form. Row echelon form is fine. You don't have to go all the way to reduce row echelon form. So you now count the number of non-zero rows. That will give you the rank of the matrix. Thank you so much for listening. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I thank you very much. If you haven't subscribed, go ahead and subscribe right now. Hit the notification bell so you can always get alerted each time a new video is released. Having done that, of course, you can also become a member of the channel by clicking on join. That gives you some special privileges as you will see when you click on join. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.